So I've started recording. Welcome to the class. Today we will be uh, continuing our discussion on electric vehicles, and let me quickly summarize things of what we had discussed in last couple of classes, and then we will start discussion on the batteries today. Then we will move on to a little bit on the uh, automotive powertrain so that we can get current onto the system. So if you were to quickly go through on the section on electric vehicles, this is what we said last time, that these are the performance requirements for the vehicle which we are designing. First is the maximum acceleration, then maximum longitudinal speed, gradability, fuel economy, and uh, then the range. So later on, we looked at the powertrain layout where we have a prime mover, uh, which can be the internal combustion engine or the motor or both, which generates the power and that goes through a transmission, which is then reaching to the driven wheels. Right. So in this case, we look at the need for the transmission as well, where we said that this is the ideal traction hyperbola which we would like to reach or approach, that is drawn between the tractive force and the longitudinal speed, and an IC engine's performance is by and large this way. So we will use gears in order to reach as close to this ideal traction hyperbola as possible. This is why we require gearboxes in IC engine vehicles, whereas we can do away with fewer gears or just one reduction gear on the electric vehicle. Then we were looking at energy efficiencies in the electric, uh, sorry, then we looked at the efficiencies in the IC engine, where we looked at different losses of how where all the power is getting lost before it reaches the wheel. And then we had a comparative study of the IC engine as a source and hybrid electric vehicle as a source, where we summarized that we got total energy remaining at 16 units versus 66 units in the hybrid electric vehicle. Then quickly moving on, we had this classification where we divided the powertrain into internal combustion, electric, hybrid electric, and plug-in hybrid. The electric vehicle further classifies into pure electric and EV with a range extender, and the hybrid electric branches out into serial hybrid electric vehicle, parallel hybrid electric vehicle, and series parallel. So these are various combination in which the two sources, the IC engine as well as the electric motor, are being connected. So then we looked at different uh, architectures, and finally we defined degree of hybridization, where we go from pure engine drive to pure electric drive with different levels of contribution of power coming from the electric part and the conventional powertrain. So in the previous section, we discussed few things about the motor characteristics and how the electric motor is different from that of an IC engine. So we said that this torque versus speed curve for a typical motor, where up to a speed called base speed, we have full torque, and the power keeps changing. Whereas from this point, we switch to a constant power region, where the torque starts decreasing as the RPM increases. Then we looked at various formulas on how does this motor power parameters relate to its requirements on the maximum speed, then gradability, acceleration performance, and we had a decent discussion on regenerative braking in the last class. And then we had also discussion on cooperative uh, braking, where we uh, yeah, Ronak, unfortunately there was some issues, but I checked it today and it has been uploaded. I will double check, but I think I have uploaded it today. So, yes. Anyway, let me check my YouTube studio that it has uploaded or not. Yeah, I think the video is up now. Just okay. All right. So yeah, then we had discussion on the regenerative braking, where let me quickly switch to. So we said that these are the requirements from regenerative braking. First is to recover energy, and second is to retain vehicle stability. Then we categorized the components where in the energy recovery aspects, we wanted to look at the battery, the motor, and the power electronics. And in the vehicle safety, we wanted to look at the vehicle, of course, which consists of these entities, and the environment like tire road interface, and the vehicle would also include brakes. So then we said that vehicle stability can get compromised in case of a wheel lock, and that is where we said that we will have further discussion on anti-lock brake system when we discuss the braking aspects. Then we said that we have wheels, the motor, the power electronics, and the BMS plus the battery system in the case of a pure electric vehicle. Our objective is to recover maximum amount of kinetic energy of the vehicle while meeting the driver demanded deceleration and ensuring vehicle stability. So in doing so, we asked two questions. First is that is the demanded deceleration achievable by regenerative brakes alone? If it is, then we said let's go ahead and use regenerative braking. Otherwise, we'll include friction braking. And then we say that if in case friction brakes are required with regen, how much of requirement is fulfilled by which type? And then we looked at certain limitations originating from these three aspects like the motor, power electronics, and the battery plus BMS, where we said that the maximum power limit uh, comes from the motor, that is maximum braking torque achievable by the motor. Then we said maximum power the power electronics module can process. And then depending on the battery, can we can the battery actually take in some more energy? We wanted to take a look at state of charge of the battery for that, and then we said let's also take a look at the charging power limitations. So this is what we discussed in the previous session, and then now coming back to the discussion I wanted to have today, that is on the uh, batteries. So yeah, today we will be discussing uh, some things on the batteries and see how it goes. All right, so a battery is an energy storage device. To make a battery, we need one or more than one cell, of course. And the cells are connected in different configurations, that is in series and in parallel. When we connect the cells in series, yeah, so yeah, we do not have this as a part of course. We started this on request, and today will be the last session on the battery portion. I did not want to repeat the exact same theoretical aspects which are already recorded in the class. So we thought of going ahead and adding some more material. Yeah, so it's not part of your syllabus, but we'll also get back to more mathematical problems later. All right, so yeah, coming back. So connecting the cells in series would get you higher voltages, but it'll have the same current limitations. Whereas connecting the cells in parallel would give you the capacity to drive high current loads, but at the same voltage limit, same terminal voltage as that of a single cell. So we can have cells connected in series and parallel in order to obtain a configuration of a battery which will deliver the required amount of current, required amount of maximum current at the desired potential difference. So the cell uh, is one entity which converts the chemical energy uh, to the electrical energy, and it contains uh, three things: a positive electrode, a negative electrode, and an electrolyte. So the chemical reaction between these electrodes would result in the energy output, that is, will have the flow of ions inside the battery, which would then enable the flow of electrons outside the battery, which gets completed to the circuit, which we uh, have by including the battery and the load. So the rechargeable battery is one such battery where these chemical reactions can be reversed. That is, by if we reverse the current, then we can charge the batteries, which would essentially takes the reaction in the other direction. So the examples of such batteries are lead acid batteries, the nickel iron batteries, nickel cadmium, nickel metal hydride, lithium polymer, lithium iron, sodium sulfur, sodium metal chloride, and then we have air batteries like aluminum air and zinc air. So we'll take a look at most of these batteries a little bit, and then we'll move on to uh, some more discussion I had on thermal need for thermal management in batteries. So yeah, uh, the battery can be modeled in this particular way. There are several cells connected. There is some internal resistance of the battery and there is an external load. So cells have nominal voltage and are connected in series to require the to deliver the required load. So the terminology is given here, and we want to minimize our R so that we can reduce the uh, redu- we can reduce the thermal losses going inside the battery. So the open circuit voltage E is affected by the state of charge, temperature, and so on. This will also depend on the health of your battery. So coming to the charge, we denote it in amp hour or ampere hour capacity. So we are saying that the charge delivered when 1 ampere of current that flows through 1 second is 1 coulomb. Uh, Here we say that in amp hour, the charge delivered when 1 ampere of current flows through 1 hour of uh, time through the circuit. So in theory, a 10 ampere hour battery should be able to deliver 1 ampere for 10 hours or 10 ampere for 1 hour. But the capacity would depend also on the discharge rate. So the C rate indicates the charging and discharging rate of the battery. So if uh, you say that a battery is 1C rated, that implies that the discharge current would discharge the entire battery in 1 hour. If a battery has capacity of say 50 ampere hour, then this implies there would be the discharge current of 50 ampere and so on. So the charging capacity of the battery is completely specified by its ampere hour rating and the C rate, the rate at which it can deliver the current or take in the current. Then we are looking at the energy stored. Here we generally use watt hour, or in our cell phone case so yeah, we can of course write it as watt hour, and I think in cell phones we write as milliampere hour. So uh, yeah, the energy stored would depend on the voltage as well as the charge stored. So energy in watt hour is V into C. The actual energy stored would also depend on the discharge rate, since V and C depend on the same. So let's quickly go through few definitions, like specific energy. This is the quantity of electrical energy stored in the unit battery mass and has the unit of watt hour per kilogram. So you're asking how much energy 1 kg of battery can hold for us. If the required energy capacity is known, it can be divided by specific energy to obtain a rough value of battery mass. Although battery mass would also include other protective layers, right? And then the second thing is energy density. By volume, how much of electrical energy can we store? So the quantity of electrical energy stored uh, for unit battery volume is energy density, and we can have it in watt hour per meter cube. So specific power is the quantity of power obtained per unit battery mass, and it's given as watt per kilogram. Now there are some batteries which may have higher specific energy but lower specific power, or vice versa. So these batteries can store good amount of energy, but it would discharge slowly. So we can have high specific power but have low specific energy as well. So we can deliver uh, a quick burst of power, but will not be able to do it for much longer. So coming to Ragon plots, here we have a plot which is against the specific power versus specific energy, and this can be used to characterize batteries, right? Uh, we are using logarithmic scales here to cover long range, and this this plot tells that the lead acid battery uh, will have a long range of specific power and the specific energy, and the specific energy is varied in this range. So it kind of becomes difficult to ascertain what is the specific power of a battery, and of course it would also depend on the discharge rate. But these kind of plots will help us in figuring out which one would suit the application. Then we have few other things like energy efficiency, how much energy we supply versus how much we get out, and the self discharge rate. So if we leave the battery without any use, slowly it kind of discharges and degrades, because the ionic movement keeps on happening inside the cell anyway. So the cell and the battery geometry would also have impact on batteries. Like these cells are typically round, or we have rectangular. Battery packs are typically rectangular blocks, although the cells inside it may be cylindrical. So now let's take a look at various types of batteries, like the lead acid battery. Here the negative electrode is lead and the positive electrode is lead oxide. The electrolyte is sulfuric acid, and in which these two plates are immersed. So the reaction here is given as follows. Lead reacts with lead oxide using the electrolyte to generate 2Pb SO4 plus 2H2O. So when we switch on the charging for this battery, the reaction goes in the reverse direction. In doing so, we would get the current outside. So these cells have by and large 2 volt nominal voltage. So there would be 6 cells in a 12-volt battery. So this battery has low internal resistance, and we can say it's around 0.022 ampere, sorry, ohms per cell for 1 ampere hour capacity. So we can use this internal resistance for one cell to figure out the internal resistance of a battery using this. So of course in the battery there will not be one single reaction, there will be more than one reactions happening. Some of these reactions are called parasitic reactions or unwanted reactions, which result in degradation of the battery. So in this case, lead and lead oxide are not stable in sulfuric acid and they slowly decompose, resulting in the self-discharge of battery. This kind of reactions also occur faster when the temperature is higher. So these self-discharge reactions do not occur at the same rate in all the cells, and it is a result of few cells being overcharging. So we are saying that when a cell is overcharged, in this particular case, there is a chance of gassing where we are producing gases like hydrogen and oxygen. This would further lead to degradation of the electrodes. So we'll come to detailed look on the electrodes after some time in the thermal management portion. So since we are taking our electrolyte and it's going into gaseous form, there can be loss of electrolyte. So previously, in older lead acid batteries, if you remember, there used to be uh, provision to add distilled water so that we can uh, keep it running for longer time. So in the new seal designs, these gases are allowed to recombine to form as water. We are in our general vehicles, we do have lead acid batteries which are used for starting lighting and ignition purposes. But the energy stored in one, the energy stored or the density of this battery, energy density of this battery does not make it suitable for electric vehicle applications. Another problem with lead acid batteries is that of sulfation, which reduces battery life. This happens when the battery is left in discharging state for a longer time, due to which the lead sulfate on electrolyte on the electrodes forms into large crystals. So, if we were to take a look at this reactions which are happening in the battery, these happen on the electrode on an interface called uh, just one sec. Uh, so, one second. Hello. Yeah. So these kind of reactions would happen on the interface where the electrode meets the electrolyte. There are the electrodes by and large are porous so that we can increase the surface area at which the reactions for the battery would occur. But then if you have crystals of unwanted material getting formed at the reaction sites, then the effective number of reaction sites gets reduced. In such a case, since the reaction sites gets reduced, the capacity of battery to give uh, current to its original design capacity reduces. Right, and this is what ends up reducing the battery life. Moreover, certain reactions would also cause corrosion on the electrode, so as to again reduce the sites at which these reactions would occur. So all these things not only reduces the sites for reaction, they also increases the resistance for the ions inside the battery, inside the electrode to actually reach the inside the electrolyte to actually reach the electrodes. And in such scenarios as well, uh, the battery life gets reduced. So in this case, typical battery life is around 700 cycles for cars with a greater battery load charge, and it's much larger for industrial vehicles. So the lead acid battery should not be charged at too high of a voltage, since this may lead to water loss. And then there are multiple steps charging right, where cell voltage is raised to a predetermined level, and then the current is switched off. So in this case, we keep increasing the charge step by step. So the limitation this battery has is that it has low specific energy, and we cannot use them for uh, long range vehicles. Next would be the batteries based on nickel, where nickel is used as positive electrode. These class has nickel iron, nickel zinc, nickel cadmium, and nickel metal hydride batteries. Amongst these, nickel metal hydride shows the most promise, and the nickel zinc batteries have very limited life cycle. These batteries have nearly twice the specific energy of the lead acid batteries, and in this kind of case, the nickel oxyhydroxide is the positive electrode, and the metallic cadmium is the negative electrode. So the reversible reaction goes as follows. During this reaction, the water is lost from the electrolyte, and hence this electrolyte becomes more concentrated. So the advantages of nickel cadmium batteries is that they have high specific power, they have significantly longer battery life, up to 2500 cycles, as opposed to the uh, around 700 to 1500 cycles on the lead acid batteries. They have low discharge, and they can operate at much wider range of operating temperatures. They are good solution for long-term storage, and they can be recharged within an hour up to 60% of right, and up to 60% of its capacity in around 20 minutes. The limitations here is that each cell voltage would be around 1.2 volts, and hence 10 cells would be needed for a 12-volt battery. So we would require more material to get to the same capacity. Uh, Moreover, the cost of cadmium is higher, and it is also a carcinogen, and it also has higher internal resistance of 0.06 ohms as opposed to 0.02 ohms in the lead acid batteries. Then taking a look at nickel metal hydride batteries, here we have the positive electrode as nickel oxyhydroxide, and the hydrogen is absorbed in the metal hydride, that is the negative electrode. So electrolyte is water, and the OH minus ions, they do not it does not change due to charge or discharge. This implies that the internal resistance and the open voltage circuit of the cell largely remains consistent. So in previous case, uh, here, since we are losing out the water in the electrolyte, the concentration would increase. As the concentration increases, the ionic mobility inside the electrolyte would decrease, and then this would uh, result in higher internal resistance of the battery. But in this case, uh, the water and the OH minus ion concentration does not change. Right, it does not change, and that results in consistent internal resistance. So during discharge, the hydrogen reacts with the OH minus to form water and releases electron at the negative electrode. Okay, so and at the positive electrode, this nickel oxyhydroxide would react with the positive with water to produce this and the OH minus ions. So at one electrode, the OH minus ions are getting consumed, and the other one it's getting produced. So all right, so the concentration of OH minus ion and the amount of water does not change. In these batteries, cells must be must be sealed so that the air does not enter in, and we say that similar performance as nickel cadmium, but and it will have the nominal voltage of 1.2 volts per cell. The nickel metal hydride can be charged faster than the nickel cadmium. However, cooling is necessary since the bonding of hydrogen to the metal at the negative electrode during charging is an exothermic reaction. Yes. So if this reaction is an exothermic reaction, we also need to be careful that the heat generated during the charging process will also attract and speed up the unwanted reactions in the battery. So the nickel metal hydride has slightly higher energy storage capacity than the nickel cadmium battery, but it has higher self discharge tendency as well. Then we have sodium based batteries that use liquid sodium as negative electrodes. They can operate at higher temperatures and use a solid ceramic electrolyte. Since they need to operate at higher temperatures, they are practical for large systems. So the negative electrode is molten sodium and the positive electrode is molten sodium polysulfides. The electrolyte is solid beta alumina ceramic which conducts the sodium ion. So uh, one coming change here is that we have ceramics as the electrolyte rather than the liquids like sulfuric acid and water in the previous one. Job of the electrolyte is to essentially help ions going from from one electrode to the other inside the battery. So the cells are connected and placed in an evacuated case to prevent heat loss. The battery needs to be heated to its working temperature between 300 to 350 degrees Celsius. And the chemical reaction is shown as follows. So some amount of sodium combines with sulfur to generate sodium sulfide that results in the electrical energy. Since these kind of batteries require good thermal insulation, they affect the practical application. And you can consider in terms of electric vehicles, if you want to have these kind of batteries which also requires uh, thermal insulation to a large extent, then we would, moreover, we also need the heating source because we have to heat it around 300 to 350 degrees Celsius. Uh, increases the weight, and the battery itself would require some energy to start working, which may not be feasible uh, for practical applications. Then there are sodium metal chloride batteries. So as you can see, we are going closer and closer to the lithium side because sodium is just after lithium uh, in the class of metals. So here the positive electrode is solid nickel chloride and the negative electrode is molten sodium. There are two electrolytes in this case, beta ceramic solid electrolyte surrounding the sodium and sodium aluminum chloride liquid electrolyte. So here the reaction given is as follows. Sodium reacts with NiCl2 to give nickel and NaCl, that is the common salt. The operating voltage here is around 2.5 volts and it would drop to around 1.6 volts during discharge. This battery need not operate at higher temperatures. Sorry, yeah, they need to operate at higher temperatures. So it also requires heat insulation and heating when not in use. Next are the lithium polymer batteries, where the negative electrode is lithium metal and positive electrode is a metal oxide. The lithium metal combines with the metal oxide to form lithium metal oxide and release energy. Solid lithium electrode results in decreasing performance due to passivation and also safety issues. So this issue is taken care of by the use of lithium ion batteries. This is a family of rechargeable batteries where the lithium ion moves from the negative electrode to the positive electrode during discharge and vice versa. Anode is generally a carbon material, graphite, that has sites to contain the lithium ions so that we can safely store the lithium ions. And cathode is a metal oxide like names given here as lithium cobalt oxide, lithium iron phosphate, lithium manganese oxide, lithium nickel manganese cobalt oxides, like these. So the electrolyte is lithium salt in an organic solvent, and this is the reaction amongst the same, where M denotes a metal. A non-aqueous electrolyte is used since lithium reacts with water. Hence, a good sealing is required to prevent water entry into the battery. Lithium-ion batteries have higher specific energy, so they are smaller and lighter. These batteries can operate over a wider temperature range with high energy density. And here, the nominal cell voltage is around 3.5 volts. Yes, yeah. Then coming to the metal air batteries, these batteries cannot be recharged since the chemical reactions in them are not reversible. So the spent metal electrodes are either replaced or reprocessed. These can be considered as the fuel that is replenished in this class of batteries. So there are, uh, in this case, the electrolyte is also typically replaced. So here in the aluminum air battery, negative electrode is the aluminum, positive electrode is porous metal mesh that has layer of carbon. Electrolyte is alkaline solution, typically potassium hydroxide, and the reaction is given as follows. Aluminum reacts with water and the oxygen in the air to form this, and the use of oxygen is why we call them as aluminum air batteries. So the aluminum electrode becomes smaller as the reactions proceed and it's replaced when appropriate. The main limitation of this battery is that it has a low specific power around 10 watt per kilogram. Then we have zinc air batteries where the negative electrode is solid zinc, positive electrode is a porous mesh, and electrolyte is liquid alkaline solution. Here the electrical energy is obtained when the zinc combines with oxygen from the air to form zinc oxide. It has higher specific power than aluminum air battery, nearly an order of magnitude or more. Then we have supercapacitors or ultracapacitors. The idea here is to provide short burst of energy, sorry, a large burst of energy in very short amount of time. All right, yeah. So supercapacitors or ultracapacitors have high specific power but low specific energy. So these can be utilized in cases where you want to store a lot of energy coming in during regenerative braking, or you want to give a boost while accelerating rapidly. The energy stored in this capacitor is half CV square. Right, the voltage across capacitor is low. Hence, capacitors have to be connected in series to store charge at a reasonable voltage. However, this reduces the capacitance but increases the energy storage capacity, which is proportional to V square. And there is charge equalization circuits that ensures that the voltage across different capacitors are nearly the same by transferring charge from those with more charge to those which are having less charge. By these, what we mean is that we will balance out the charge across capacitors by transferring charge from one of the uh, capacitor which has more charge to the one which has less charge. Essentially, we should be calling it as transferring energy from one capacitor to another one. Then we also have flywheels as energy storage devices. Yes, Sandeep, you can ask a question if you want. Yeah, so like supercapacitors, flywheels do have high specific power but low specific energy. Mm, can also be used to store the energy in form of kinetic energy, and it can be released when the flywheel slows down. But here, the mechanical stresses also increase as the speed increases. All right, so I think that is all on the energy storage aspects. But today I also wanted to have little more discussion on some notes I found, which I wrote long back, on the need of thermal management. So I will be sharing these notes, but I will also go through few of the illustrations. So this is the data. Again, apologize for the source. I was an undergraduate at that time. Uh, these are the type of application, then uh, places where it was used, and the incident summary, like what went wrong. So in this case, the internal short circuit in defective battery pack due to insulation damage between battery cells and wall of the aluminum container. Fire occurred after, in this Second case, there was fire occurred, which was after 3 weeks after a crash test. In the Nissan GT case, electric arc caused by short circuit of high voltage distribution lines and the car body ignited combustible material in the vehicle. In the Boeing 787 Dreamliner, I think this was quite old, battery overheated and started a smoky fire. In this case, a battery error malfunction was, sorry, an error message indicating battery malfunction was flashed and odd smell was detected in the cabin. So essentially, this data gives us insight into various lithium metal battery related uh, mishaps which has happened. So we have something called thermal runaway, which can cause due to various aspects. Right, thermal runaway can result into consequence of smoke, fire, and or explosion, or a combination of these. Thermal runaway happens due to various aspects. First being mechanical abuse, electrical abuse, thermal abuse, and contamination. In mechanical abuse, if we have deformations happening to the cells due to like crushing or penetration, then this would result into the separator tearing apart. So a battery is generally made. In last class, you had shared a link on carburation. Yes, can I post it on the YouTube video itself just below that? I will do that in some time. Thanks. Yeah, so as I was saying, uh, the way batteries are constructed are something like this. Let me quickly draw it for you. Okay, so we have different sheets of objects. So let me draw it with different colors. So this is your positive electrode, this is your negative electrode, and in between two there is a separator. Okay, battery construction. So you have these three entities, and the electrolyte is uh, filled between the two. Right. So you can think of the separator soaked in the electrolyte, and each of them as a just to assist you with the mental picture, like a cloth. Okay. This is electrolyte. So what we do is, uh, imagine you have three handkerchiefs, one with one which is made of the cathode material, one which is made of the anode material, one which is made of the separator material, and the separator one is soaked in electrolyte. So the separator's job is to keep these two electrodes uh, essentially separate from each other. Then we have the battery essentially starts as a sandwich of these three so-called handkerchief, and then it is folded across, right? Again and again on top of one top over the other, so that the things do not touch each other. Right? That is, the two electrodes does not touch each other. But what would happen in case of a deformation or a penetration? This kind of a separator tears off. If the separator tears off, this would result in the internal short circuit of the battery. Right? If there is internal short circuit, inside the battery, it would result in very high current loads. Okay, since the current inside that battery would start going very high, the temperature would also increase and it has a chance of starting a fire inside. That is the separator tearing aspect. Then we have electrical abuse. So as we said and looked into the case of lead acid batteries, we can say that in the lead acid battery, there was formation of what sulfur oxide crystals, if I remember, right? So let's quickly check that. Right. So yeah, sorry, my bad. Which led to formation of lead sulfate on the electrolytes into large crystals. So these crystals will grow due to overcharging or over discharging onto the electrolyte surface. Sorry, on the surface of the electrode. Now this growth of dendrite structure also has potential to pierce through the separator. And again, if the separator gets pierced due to this dendrite growth, it amounts to micro tearing of the separator. And again, it would result in internal short circuit. And same story because of high temperature, because of overheating. So, for example, either because of reason 1 or reason 2 or contamination, if one cell gets heated up because of internal short circuit, the temperature around it would rise. If the temperature around one cell rises in the battery pack and the battery pack has several cells next to each other physically, the temperature increase because of internal short circuit in one cell would result in overheating of the cell in the neighborhood of that particular overheating cell. This thing essentially amounts to uh, it gets similar to that of one bad apple spoils the batch, right? So the heat would go on increasing. That would result in thermal runaway. Sorry, this overheating would result in separator collapsing, which would again have internal short circuit. So if one battery cell gets damaged, there is a likelihood that the cells packed next to each other, next to that first damaged cell, would start getting damaged, and there is a risk of thermal runaway. Okay, so a brief note on aging of battery. Again, I'll share these notes with you. Battery aging can be characterized into two parts: calendar aging and cyclic aging. So calendar aging reflects again, the calendar aging is called in a way that because the performance drops in the battery when it is kept on the shelf. As well, when we say the battery is having cyclic aging, that means we are using it actively. Cycling aging depends on factors such as depth of discharge, temperature of operation, charging and discharging voltages, and the time taken for charging and discharging. Then we are looking at the mechanisms of heat generation. Why does the battery has heat? Right. So, as I have written here, if we reach to the position of a thermal runaway, as we discussed due to the three reasons or four reasons in the previous illustration, a series of chemical reactions will raise the internal temperature and pressure until the battery bursts into flames. Right, so heat generated inside the battery can be categorized as the reversible heat and the irreversible heat. So these are the ways. Of course, for heat dissipation outside the cell, there are three options for you: conduction, convection, and radiation. Then heat generation has two mechanisms: the reversible one and irreversible. So the reversible heat, its source is entropic and hence can be recovered when the reaction is reversed during charging. Then there is irreversible, which comes from overpotential, phase change, and mixing and dissipating. So these kind of things. Also, in overpotential, there are ohmic losses, charge transfer at the interface, and mass transfer limitations. So let's take a look at the irreversible heat. So let's consider this illustration and try to interpret. Here we have on the x-axis voltage, and on the other side we also have the temperature in the red. We are looking at uh, three different levels. In level 1, we are having self-extinguished behavior. That is, then we have level 2, which depends on heat dissipation, and level 3 is thermal runaway. So we'll not directly go to thermal runaway with each kind of things happening, right? So if the temperature starts rising, the battery may show self-extinguishing behavior, or there may be adequate heat dissipation mechanisms around the battery, which will enable you to uh, keep up with the heat getting generated in the battery and may not result in thermal runaway. But sometimes uh, we can look in level 3, you are left with no voltage, and it's too late for the battery. I think one illustration I wanted to show, uh, yeah, so formation of solid electrolyte interface. So this is one more important topic, which is something you can understand about the batteries. The solid electrolyte interface, or SEI, forms as the electrolyte interacts with the electrode at the electrode electrolyte interface. So in lithium ion batteries, this SEI forms when lithium ion reacts with the graphite at the anode and forms a layer. So this layer is essentially SEI. It forms on both the electrodes and it results in dissolution of electrode into solution. So if we call the active material, which essentially takes part in the reactions for uh, providing the power to the outside circuit, this solid electrolyte interface formation reduces the active material and it takes up the site. So if you have anode and the electrolyte, this is how the solid electrolyte uh, interface would form. This would decompose during charging and discharging, but each cycle of charging and discharging will leave out a little bit of SEI. Right, if the depth of discharge increases, that is, you have discharged your battery a lot, or if you have increased it due to overcharging, the thickness of SEI becomes thick enough that it could not be broken in upcoming cycles, right? So, although this SEI decomposes and regenerates because of electrical abuse of the battery, there is a chance that we will not be able to break it down completely. So this may result in rendering the battery useless. And this SEI would also provide barrier to ion transport through the diffusion. That means, to complete the flow of electron in the outside circuit, the ionic transfer must occur inside the battery. And if this SEI starts providing barrier to ion transport, that is, it cannot go from electrolyte to the anode, then in such scenarios will not be able to provide sufficient current, right? And since there is the resistance to the transport of ion, it would also result in heating. So this is one of the pictures I found for the solid electrolyte interface and the electrode electrolyte interface, right, where you can see the graphene skin and the dotted line is the SEA at the electrode interface. So I think, yeah, with this I can wrap up the discussion on SEA formation. I thought which would be a good information to have. So, all right, I think we can have a discussion and something. Uh, if you have any questions, we can have a talk on that. Mhm. Hello. Hello. Uh, Hello. Yeah. Hello. Hello. Are there any questions which you would like to discuss? Hello. Uh, okay. Ronak, I have uploaded the week 3 video, and the first comment on that links you to the video on the carburetor, so you can take a look at it. I hope that would be helpful. I encourage all of you to take a look at it. It's one of the beautiful videos, which will show you in a transparent carburetor how a carburetor works. So I think it's going to be helpful in improving your understanding. So if there are no more questions, let's quickly discuss the agenda for next week so that. All right. So today, for us, it was week 4, and instead of going through the same material again, which is by and large this course has theoretical component, we moved on and had our sessions on electric vehicles. Uh, for now, I think I am done with the. We also need last class link. Yeah, just 1 second. This is the link for last class. Right. Yeah, I'll paste it here. That's my YouTube channel. You can get all the links here. Right. I'll upload in the Excel sheet as well. I'll do that in 5 minutes, but it's essentially on the same channel. So the next week for homework would be automotive clutch, transmission, and power analysis. So we will be doing a problem solving session next week for the clutch, transmission, and powertrain analysis. Although it will say the week 5 session, essentially we will be covering syllabus as given in week 6. Right. So we'll do one assignment on or one set of problems on this, and in upcoming weeks we will start looking at the week 7 aspects. We'll start discussing the brake systems. uh, as I have previously said, brake systems are part of my core research, so I will be showing you some discussions and results and latest research we do at IITM on the anti-lock brake system. So although up to yeah, so next week we will be discussing the transmission problems. Then next couple of weeks we will spend uh, in having in-depth understanding of anti-lock brake system and the brake system in general. Right, and I would also take some time in that to introduce you to the control system aspects of it a little bit. Then we'll try to continue after the anti-lock brake system. We'll have a braking analysis portion, and then we'll move on to the steering part where I will show and demonstrate the Ackermann steering geometry as you would be taught in the classroom and how it translates to a real application, and some bits and pieces of assignments I did on steering design so that we can have some more understanding there as well. Uh, so roughly speaking, next week we'll look at transmission. Post that, we will spend 2 or 3 weeks in depth in understanding the anti-lock brake system. And of course, any questions on brakes you have in those moments, I would strongly encourage you to ask, as I would be better equipped to assist you and answer you regarding the same. So, if we do not have further questions, we can perhaps stop the recording. Yes, Ronak. So whatever we discussed in last 3 sessions, right, for the hybrid electric vehicles and the motor section last week and this week's batteries, not part of this course on NPTEL. So uh, that is not something you need to prepare for your exams, the NPTEL exam, which you might have registered. Yeah, these are just for understanding, and actually, so this course was recorded quite some time ago, right? I think if there is a date on when exactly it was recorded, that they are not telling us. It's been a while since the course was recorded, and this was pre-pandemic also. After recording this course, we started running more module on electric vehicles, which was not run in this version of the course. So whatever was taught in IIT last semester and what we will be teaching next semester, yeah, 2019. So the latest edition of 2022 included the section on uh, hybrid and electric vehicles. All right. So, all right. So I think that is all I have for this week. If you have any questions, you can stay back, uh, or we can end the session. All right. Thank you. So I'll wait for a couple of more minutes. Okay. Yeah. Thank you everyone for joining. I will upload the videos sooner this time. All right. Thanks.